Welcome to section 11.2, one-sided limits and calculus limits. We're going to evaluate one-sided limits. Yesterday we talked about how a limit didn't exist unless it approached the same value from both sides. And then we'll also learn a little bit more of the algebra side. We're going to learn different techniques to find limits of functions. So those are our two things that are going to focus on. The first part is one-sided limits. Now yesterday we talked about how a limit exists, but if it approached the same value from both sides. But on one-sided limits, we're only looking at a specific side. So for example, limit of f of x as x approaches c from the left side of the graph, or the negative side, it's written the same way, but you notice that x is approaching c, and then there's this little negative sign. That indicates that you're approaching it from only the left side. And so you can answer that question, but only from the left side of the graph. And then you can turn around and do the same thing. From the right side of the graph, or the positive side, then we'll do as x approaches c from the positive side, which will have a plus sign. So kind of same notation, but you'll see a little extra part here indicating that it's a one-sided limit instead of just a regular limit. On the next part here, let's move that up a little bit. So find the limit left and right of 0. So the function is f of x equals the absolute value of 2x over x. Now, I already have this one graph on the notes, but if you want to go to your calculator, you can do the absolute value. You have to go under math, and it should be under number. Usually it's the first one, ABS, and you'll do the absolute value of 2x, and then we're going to divide that by x. And so what we get is this. Alright, let me zoom in a little bit. Okay, so you saw that on the note handout, or in the note sheet, so let's kind of go back to that, but this is what it looks like. And so, do that a little bit. So what we see here, and these lines do go on, what's happening here? I mean, all these values, because of the absolute value, are either positive or negative, and then there's this shift, and these are both open circles here. At 0 it's undefined because the denominator cannot equal 0. So those are both open circles. So what is the limit? Well, let's look at the couple things I'm asking for. The limit as x approaches 0 from the left side. So from the left side, the negative side, as we get closer and closer to x equals 0, and x equals 0 right here, this right here is at 0. So as we get closer and closer to 0, what is the y value getting closer and closer and closer to? Well, in this case, it's actually staying at -2, but it also approaches -2. So it's getting closer and closer to -2, and it's actually staying at -2. Remember, we're not interested in what happens at 0. We're interested in what happens as it gets close to 0. So it stays at -2 the closer and closer it gets to 0. From the right-hand side, so as we're looking at the right-hand side of 0. So same thing, as we get closer and closer and closer and closer to 0 on this graph, what is happening to your y value? Well, it's at 2, it's at 2, it's at 2, all the way down. And as we get close to 0, it stays at 2. So the right-handed side of this limit is equal to 2. So the left-handed side is -2, the right-handed side is 2. Well, if we go back to what we did yesterday, then what's the limit as x approaches 0? Well, because it approaches two different values, then what do we say about the limit? It does not exist. Why? Because it approaches two different values. And so you got to explain that when the limit doesn't exist. So an existence of a limit. If f is a function and c and l are real numbers, then the limit exists if and only if both the left and the right limits exist and are equal to the same value. So really what we talked about yesterday, just kind of fine-tuning that and explaining, the left side, the right side, they have to be the same for the limit to exist. In this case, that's not true. So let's move on to another graphing one. Find the limit of f of x as x approaches 1. So let's go ahead and graph, and then we'll go from there. So we want values that are less than 1. So we're going to graph 4 minus x. And you don't have to do a t-chart, but I'm just showing you kind of the visual wise. We got 1, we want values less than 1, 0, negative 1, negative 2. If we plug those in, 4 minus 1 is 3, 4 minus 0 is 4, 4 minus negative 1 is 5. And so the slope is negative 1. So as we go to the left, you can see the numbers going up. So at 1, 3, now it is open, because it's not included, 0, 4, negative 1, 5, negative 2, 6, and so on. So let me get a line here. Alright. And then on the other one, we have 4x minus x squared, and we want values that are greater than 1. 1, 2, 3, 4. I know 1's not included, but that's my starting point. So if I plug 1 in, that would be 4 minus 1 is 3. Plug 2 in, 8 minus 4 is 4. Plug 3 in, 12 minus 9 is 3. And if I plug 4 in, 16 minus 16 is 0. So let's see what I get with that. So 1, 3, still open, so I don't close it in. 2, 4. 3, 3. So the graph is opening down. You can see that because of the negative x squared. And then 4, 0. Okay. And so the question that we're trying to answer is, what is the limit? We'll just do the limit of f of x. And let's do all three. We'll do the limit as x approaches 1 from the left. We'll do the limit of f of x as x approaches 1 from the right. And then our final one is what is the limit? So we'll do the limit as x approaches 1. Just of the function f of x. So it has to be the same. So let's take a look. So as we get closer to 1, and so 1's right here, this is the x value at 1, so we want to get closer to this on the graph. So from the left side, as it gets closer, what is the y value getting closer to? You can see the y value is getting closer right there at 3, that point, 1, 3. So from the left side, it's approaching 3. From the right side, so now we're coming in on the other side, the right side, the positive side, it also is approaching that value of 3. So since these limits are the same, then the limit of f of x is also that value of 3. And that's, looking at one-sided limits to help you identify what the limit is of the function. Alright, so that kind of takes care of the first part of one-sided limits. The next part I want to jump into is a couple of algebra things that we need to cover on limits. One of the things we learned yesterday with algebra is that we could use direct substitution. Well, direct substitution is not going to work for everything because it doesn't always give you, it doesn't always exist. So we got to look at these other problems that when we solve the limit and direct substitution doesn't work. So the first one is called the divided out technique. Should be applied only when direct substitution produces 0 in the numerator and the denominator. So the first thing that we always do for derivatives, for limits, is we do direct substitution. We say, okay, and I'm just going to use ds to indicate that I'm going to use direct substitution. I'm going to plug 2 in, just like we did yesterday. And I'm going to see if it works. Well, I get 0 on top and I get 0 on bottom. So it's undefined, so direct substitution doesn't work. So we got to figure out another way to do this. And as I said, one of these is divide it out. So we want to divide these two numbers. Now, long division, synthetic division, what are we dividing here? Well, the other way that we can also divide is just to cancel common factors if things can be factored. And when you get this 0 over 0, something can cancel out. That's why that's occurring. So we're going to go back to the limit as x approaches 2, and we're going to factor it. So we got a difference of squares on top. And what you find out is we have a common factor. And that's why you were getting that 0 over 0. And so we cancel those out. And if you think back to rational functions, what is happening at that value of 2? Why did direct substitution not work? the reason direct substitution didn't work was because there is a hole in the graph, and so it's undefined. But once we cancel that out, remember when we found the hole in the graph? We canceled, and then we plugged back into the simplified version because it wasn't undefined anymore. Well, same thing here. Now that it's not undefined at x equals 2, we're going to use direct substitution again. Now when we plug it back in, it's not undefined, and we get 4. So the limit of this function as x approaches 2 is equal to 4. Very similar to what you guys have done in the past with holes in the graph and points of discontinuity. Okay, factoring and canceling. Alright, B, we got a cube root, we got an x cubed minus 8 divided by an x minus 2. So I'm going to show you how to factor a difference of cubes if you have forgot. But before we do that, we need to do our direct substitution. Plug in, once again, it looks like we're looking at the limit as x approaches 2. And we get 0 over 0 again. So we have to do this part before we do anything. And then now we can go through and factor. So x cubed minus 8. These first two represent the cube root of each of these. So the cube root of x cubed is x, and the cube root of negative 8 is negative 2. And then your trinomial is your first term squared, so that's x squared. Your last term is your last term squared, 2 squared is 4. And then your middle term is these two being multiplied together. So those two multiplied together is 2x. So that's where the trinomial comes from. And then your signs are same, opposite, always positive. Kind of spells soap. Same, opposite, always positive. Whether you're doing a difference or a sum of cubes, it's always that way. Same sign, so it was negative up here, so it stays the same. Now it's opposite, so it's plus, and then your last one is always positive. So if I need to go over that a little bit more in class, I can. And then you have x minus 2 on bottom. So once again, what do you see? You see that factor of x minus 2 canceling. Why we got the direct substitution of, 0 over 0 up here. And let's try to make that a 0. And so we're left with the limit as x approaches 2 of x squared plus 2x plus 4. Once again, there was a hole in the graph, that's why it was undefined. And now we can do our direct substitution again now that we've canceled that common factor. So 2 squared plus 2 times 2 plus 4. Get a bunch of 4's here. 4 plus 4 plus 4 gives you 12. And so once again, that's how you use the divided out technique. So we'll look at one more, maybe look a little different on this one, but kind of the same idea. It's just a square root that you have. We're looking for the limit as x approaches negative 3. Once again, we do our direct substitution first. So we got the square root of 2 times 3 squared minus 18, and then negative 3, and then negative 3 plus 3. So that's going to give us 9 times 2 is 18, so that's 18 minus 18 over 0, and that's 0 over 0. So we still get the same thing as 0 over 0. So knowing that direct substitution once again doesn't work, we're going to divide it out. So we have the limit as x approaches negative 3 times the square root. We can factor out a 2. That'll leave us with x squared minus 9. Okay. And then we do it again because we can factor again. That's a difference of squares. And if you get 0 over 0, something should always cancel out. That's why that's occurring, because when you plug in negative 3 here, this is where you get a 0 on top and a 0 on bottom. So those cancel, and now you're left with the limit as x approaches negative 3 of the square root of 2 times x minus 3. And so now you can turn around and plug in, do your direct substitution again. And so we have the square root of 2 times negative 3 minus 3, which would be negative 6 times 2 is negative 12. Well, go back to our definition. We are only dealing with real numbers. So when we go back, this is not a real number, so this limit does not exist. And that's because x equals -3 is not part of the domain. Okay, you can't plug it in. You're not going to be getting a value there. So it does not exist. So even using algebra, we can find out things that do not exist. All right, I'm going to show you one more technique on this one. And this is called the rationalization technique. So once again, we are going to use direct substitution to verify that we do get 0 over 0. And then once that happens, we're going to multiply the numerator and the denominator by the conjugate. Okay? Remember conjugate when you had, just to kind of give you, I guess, let's see, usually we have a plus bi, then its conjugate is a minus bi in terms of complex numbers. But same thing, if you have 3 plus the square root of 2, then its conjugate is 3 minus the square root of 2. Okay. So when we go and look at this, we use our direct substitution first. We're plugging in 0, so we get 0 over the square root of 0 plus 1 minus 1. So that's 0 over the square root of 1 is 1. And so once again, we get 0 over 0. But on this one, why does the divided out technique not work? Well, there's nothing to divide. There's nothing to factor or anything like that. So we're going to use something called the rationalization. We're going to rationalize. Typically, we rationalize the denominator. It doesn't have to be the denominator. It could be in the numerator. So we're going to multiply by the conjugate. So x over, and we're going to multiply by the conjugate. Well, the conjugate is, so the square root stays the same, square root of x plus 1, but instead of minus 1, we do the opposite, which is plus 1. And so if you do it to the bottom, you got to do it to the top to keep the same thing. And so we're going to multiply these two terms together, and then these two. So we'll get the limit as x approaches 0. Now on top, don't distribute that through, and you'll see why in a second. On bottom, I want you to, though. So the square root of x plus 1 times the square root of x plus 1 is x plus 1. Because these are conjugates, when you multiplied conjugates, even if you go back up here and you multiply these, what happens is your middle term always cancels out. So I'm not going to worry about my middle term because I'm going to get the square root of x plus 1 minus the square root of x plus 1, which just cancels. And so then I have my last term, which is negative 1. So this would give me, if I did the whole thing, it'd be x plus 1 plus the square root of x plus 1 minus the square root of x plus 1, and then minus 1. And so this is the part that I'm talking about that is canceling out, and you're just left with the x plus 1 minus 1. And so we keep simplifying, and we're left with x times the square root of x plus 1 divided by the 1's cancel, and you're left with x. So at this point, if I do direct substitution again, I'm still going to get 0 over 0. Something has to cancel. And so what do you notice that cancels? Well, this x times that cancels with this x. So we're finally left with something that has canceled out that common factor, so we can do direct substitution again. And so now that we've simplified, now we can use our direct substitution. So we say 0, the square root of 0 plus 1, that would be 1 plus 1, which is 2. So the limit as x approaches 0 of this function is equal to 2. And so that's how you use the rationalization technique. Definitely practice that one. That one takes a little bit more time, but once you get the idea of the conjugate and the multiplying, you should be good to go. Also, pay attention to how I did the notes today. Limit as x approaches 0. So first I did my direct substitution. There's no limit there because I'm doing direct substitution. Then I write my limit as x approaches 0. As I continue to do the math and the rationalization, the limit stays there all the way until it canceled. And then at that point, I'm back to doing my direct substitution. So that is very intentional as to how I'm showing my work. So make sure the limit stays as long as it's supposed to, and then when you're done and you do your direct substitution, then that's when you don't write it anymore. And then your final answer, you need to write the limit as all of that. It needs to be your final answer, not just the number 2. So that is it for today. You guys do have book work. Make sure that you do these problems algebraically, and then the 43 through 48 you're doing graphically. Okay, so once again, make sure you use algebra and then graph on the 43 through 48. Thanks.